All right, so previously we showed that you could solve this circuit by just doing KVL around each of the loops here, right? One there, there's one here, and then there's one here. And you can do KVL around those loops. You can write expressions for each KVL. You end up with IAN, IBN, and ICN as your three unknowns, and you can solve this system of equations and get the three currents. Although the algebra is very tedious, that is one way of solving this problem. The other way of solving this problem is to create an equivalent Y-connected source from our delta-connected source. Remember when we talked about when we first talked about line to neutral voltages here, I showed that if we take the voltage from the A or the B or the C to the neutral, we get one particular amplitude, right? 170 volts in this case, but we could just call it VP. And when we took the voltage from line to line, which is what we're doing when we have a delta connected source, the voltage is √3 times larger than it was in the A or the B to neutral case, right? And that is consistent with what we see in the table, which is, let me find the table here. If we look at a Y to Y system, it's saying that if I have my VA to neutral with a magnitude of VP, my line voltage VA to B is going to be √3 times larger with a phase shift of 30 degrees. So if I want to go from delta to Y, I can basically just undo that process. I can take my delta to Y, which has a VP, and then I can divide it by the square root of 3 to get the equivalent Y, because let's just take a look. If I look at this, it's telling me that from point A to point B, I basically have a particular voltage. In this case, it was 210 volts. So if I just look at A to neutral or B to neutral, it's going to be √3 times smaller. So what I can do is I can say that VAN is going to be equal to the magnitude of VAB, which is 210, but divided by the square root of 3. And then we also have to take into account that 30 degrees phase shift, right? So we're going to subtract 30 degrees from VAB, which is 0, and so we're going to get a negative 30 degrees phase shift, and that's going to be my VAN. VBN, similarly, same size magnitude, 210 angle, or divided by √3, and then the angle here, again, is going to be the angle of my BC source, which is negative 120, but I have to subtract 30 from that, so I'm going to get minus 150 degrees volts. VCN, I'm sure you could have guessed, is going to be 210 angle, or divided by √3, and then the angle is going to be 30 plus 120, which is just going to be 90 degrees. Okay, and so that is my equivalent Y-connected source. So if we wanted to redraw this circuit now, since it's gotten pretty ugly, we could do that. And we don't need to draw the delta source anymore. Notice that the connections are still the same. Right, I'm still connecting everything exactly the same, but I've just drawn my Y-connected source, and it's much easier to look at than it was with the delta-connected source. Right, so this is the neutral, this is the neutral. Of course, there's a line here, an imaginary cable there that doesn't carry any current. This goes here, just like that. This is C, this is B, this is A. And now finding my line currents or my phase currents is pretty trivial, right? 210 divided by √3, let's throw that in our calculator. And this works going the other direction, right? If we had a Y-connected source and wanted a delta-connected source, we just multiply by √3, which is what we saw in the past. But you typically wouldn't want to do that. So 121.2 angle negative 30 for this first one, VAN. And then VBN and VCN, of course, follow suit. And so if we wanted to find IA, again, let me just move this down here. We can very easily find IA because we know that it's just going to be VAN divided by ZY. So in this case, it's going to be 121.2 angle negative 30 degrees volts divided by 47.17 angle 32 degrees ohms. And I can find IA, let me throw this in my calculator, 121.2 divided by 47.17 gives me 2.57. Angle negative 30 minus 32 is negative 62 degrees amps, and that is going to be my line slash phase current, right? Of course, because this is also equal to IAN, and I can find IBN and ICN the exact same way, okay? Let me make sure that that's correct from the book. Is this the correct answer that they got? 2.57 angle negative 62. Yep, that's correct. All right, so that wraps up Module 3. Solved a bunch of example problems. You're going to have some homework problems where you're going to have to solve these kinds of problems. And if you have any questions, of course, please feel free to let me know. But hopefully all this was pretty clear. And yeah, we'll see you guys in Module 4. Really excited to be wrapping this one up. This was a pretty long one. All right, see you guys in the next module.